All right, so picking up where we left off, we're going to talk about titration. So you guys might not have ever heard of titrations before, but titrations are an application of solution stoichiometry. We're going to take a solution of a known concentration and we're going to use it to find an unknown concentration of another solution. The two most common types of titrations are acid-base titrations and oxidation reduction titrations. We're going to focus mostly on our acid-base titrations. Those are more common and a little easier to follow. So an acid-base titration is used to accurately determine the concentration of an acid or a base solution or find the molar mass of an unknown acid or base. So what you do for an acid-base titration, you take a aqueous solution of a base or an acid and you place it in a burette. So the burettes are the glassware that you guys didn't really get to work with, but they have a little lever right here that you open to make the solution come out at the bottom and you empty it into a beaker. So you're taking an aqueous solution of a base or an acid in a burette and you're slowly adding it like drop by drop to the solution of acid or base that you have in your beaker or flask. And you use what's called an acid-base indicator to change color when the acid-base reaction is complete, so you know when it's done. The most common acid-base indicator in chemistry laboratory is phenolphthalein. Phenolphthalein is a long, kind of ugly word, but it's just an organic dye that's colorless in acidic solutions and pink in basic solutions. So let me show you what that looks like. Uh, And I can't include a video in uh, my recorded video this way, so I'm going to show you my PowerPoint. So here we have a solution filled with phenolphthalein, and you add base to it. So it's an acidic solution with phenolphthalein that is colorless. You add base to it until it changes color. So there we dropped some of our base on the side, but still not enough to make it change color. And there we are, where we have enough base to make it change to pink and stay pink. Oops. I'm just going to go back to my file here. Sorry about that. I'm going to stop sharing my screen because I'm done with the video. Let me go back to the slide we were on. Sorry about this. All right, so that is how phenolphthalein works. It's colorless in acidic solution and pink in basic solution. So once you add enough base to your acid, it will become more basic than acidic and your solution will stay pink. The equivalence point in an acid-base titration is the point at which the acid or base has been completely consumed by the base or acid that was added from the burette. So the equivalence point is the exact moment where your acid and base concentrations are equal. And then any point after that is where your phenolphthalein solution will be pink. All right, so moving on, when we want to determine an acid or base concentration from a titration, we have these steps. First, you want to write a balanced equation for the acid-base reaction. Next, you want to use the volume and the concentration of the basic or acidic solution to calculate the amount of base or acid that was added to the solution during the titration. Now, after that, you want to use your balanced equation to determine the amount of acid or base present in the flask and uh, use that amount of acid or base and the volume to determine the concentration. So that sounds a little complicated, so let's try it out. So we want to calculate the volume of a 2.89 times 10 to the negative 2 molar barium hydroxide solution that is required to neutralize 10 mils of a 0.209 molar perchloric acid solution. All right, so perchloric acid. So perchlorate is one of the ions that I told you guys you didn't need to remember, so I'll just write it out for you. So perchlorate is ClO4, and perchloric acid just has a hydrogen with it. So perchloric acid, it has a molar mass of 100.46 grams per mole. Barium hydroxide is this guy again that we saw previously, and its molar mass is 171.34 grams per mole. All right. So if we have a, no, we might not have needed that at all. So if we have a 10 mils of a perchloric acid solution, I'm going to convert it to liters. And then we're going to multiply by our concentration, which is in molar. So that's moles per liter. Cancel out milliliters and liters, and we find out that we have 0.00209 moles of perchloric acid. And what did I forget to do, guys? I forgot to write my balanced equation. So barium hydroxide and perchloric acid are going to react to form barium perchlorate, which is this guy, and water. And I'm just going to tell you what the balanced reaction is. We've got a 2 here and a 2 for our water. All right, so let me erase now. So we've got barium hydroxide plus 2 perchloric acids goes to 2 waters and a barium perchlorate. All right, so now we have 0. So we found out before when I skipped a step that we have 0.0209 moles of perchloric acid. And we can tell from our balanced equation that we have a 1 to 2 ratio of barium hydroxide to perchloric acid. So that means that we have 0.001045 moles of barium hydroxide. And if we have a 2.89 times 10 to the negative 2 molar solution, that means we want to divide by that. 0.0289 moles per liter. I just converted that to standard form and not scientific form. So if we cancel out our moles, ends up with 0.0362 liters or 36.2 milliliters of barium hydroxide was required to neutralize our perchloric acid solution. All right. So titration. If you have a primary standard, you can do a standardization titration. So that is where you find the concentration of an acid or base very accurately. Primary standard. Standard is some acid or that is obtained in a pure form, such as P. Act in a 1-to-1 ratio with sodium hydroxide, and it's used as a primary standard. So we have 32.3 milliliters of sodium hydroxide neutralizing 2.533 grams of KHP. So 2.533 grams of KHP, I'm going to divide by the molar mass, which I looked up to be 2.4.22 grams per mole. So that means that we are neutralizing 0.0124 moles of KHP. And like I said, a monoprotic acid has a 1-to-1 relationship, so that means that we're using 0.0124 moles of sodium hydroxide for this neutralization. And we have 32.3 milliliters. So we take our moles divided by our volume in liters, which is going to be 0.0323 liters. And we're going to end up finding out that we needed 0.384 molar sodium hydroxide. All right. There's so much you can do with titrations. Another thing you can do with titrations is determining the molar mass of an acid or a base. So what you do for that, I'm going to go through this kind of quick because I made this part of your homework practice because you can only do so much with titrations before you get tired of it. So here we go. So we have a 0.3341 gram sample of unknown monoprotic acid. So we got that monoprotic acid term again. And it's dissolved in water and standardized with barium hydroxide. So again, we're using barium hydroxide. So the equivalence point is reached after the addition of 23.04 milliliters of this concentration of barium hydroxide. So unlike sodium hydroxide, when we have a monoprotic acid, that means it's just HX, and we're forming barium X. That means that the X is a -1, so we need 2 of them, which means we need 2 of our acid to react with 1 barium hydroxide. And we'll get into that a little bit more later in this chapter, so that makes more sense to you guys. But for now, all you need to know is that monoprotic means that it is 1-to-1 with something like sodium hydroxide, but it's 1-to-2 with something like barium hydroxide. So what that means is that we have, so if we have 23.04 mils of barium hydroxide, going to convert that into liters, divide by 1,000, and multiply by our molarity. So that we cancel out liters and milliliters. And find that that means we need 0.0201 moles of barium hydroxide. All right. And from our equation here, we see that it's, like I said, a 1 to 2. So we take our 0.00201 moles of barium hydroxide, and we're going to multiply it by 2 to get moles of our acid, which I'm just going to keep calling HX. So our moles of barium hydroxide cancel out, and we find that we need 0.00402 moles of our acid. And we knew that we had a 0.3341 gram sample, so molar mass is just grams per mole. So what we're going to do is take 0.3341 grams and divide it by 0.00402 moles and find that our molar mass should be 83.14 grams per mole. Pretty neat, right? All right, one more thing we can do with titrations. I apologize for how long this has gotten. So, an oxidation reduction or redox titration, if we take the red from reduction and ox from oxidation, we get redox, uses a redox reaction to analyze a solution of unknown concentration. And the equivalence point occurs when the reactants are consumed, which is detected by a color change in one of the reactants. So again, we see our equivalence point from a color change. So here's a reaction. This is a redox reaction. We have permanganate, one of those polyatomic ions I told you didn't really need to remember, but you might see again, and our iron 2 plus ion. All right, so those two are reacting, and we're forming iron 3 plus and manganese ion. So those ions are changing oxidation states, going from a 2 plus ion to a 3 plus ion for iron. And when we change oxidation states, that's why we call it redox titration. Anyway, so they gave us the balanced equation, and we want to find the concentration of our iron 2 plus solution. So we titrate it with 0.1971 molar solution of permanganate, and this is what we find. So we have 20.18 milliliters of permanganate, which is this MnO4 minus ion, and we're going to multiply it by our concentration, 0.1971 moles per liter. I'm going to move my decimal point over so I can cancel out milli in our milliliters. And then our liters cancel out, and we have, so this is 0.02018, because I kind of went off the screen there. So that means that we have 0.00398 moles of permanganate in our reaction. So you can see from our reaction that it's a 1 to 5. So we're going to take 0.00398 moles of permanganate, and we're going to multiply by 5. So there's 5 moles of iron for 1 mole of permanganate. Okay, I'm going to erase. So that means that we used 0.0199 moles of iron 2 plus in our reaction, and that was 40 mils of iron 2 plus solution. So we take our moles and divide by volume in liters. So 40 milliliters is going to be 0.04 liters. So moles per liter is going to give us our concentration in molarity, and that's going to be 0.4972 molar. All right, so that is all I'm going to tell you guys about titrations. I know it's a lot, and I apologize. So you will do lots and lots of titrations in Chem 120, but like I said, you will see one in Experiment 11, although you don't get to do it this semester because of our online coursework. All right, so I will see you guys in class tomorrow/today. Sorry. Good night.